I'm all right. I'm all right. Don't worry about me. I made it. Okay. Um, next, doing a few of these problems. So what we said was this is our derivative, the formula for finding it. It's going to give us our instantaneous rate of change, all the stuff up here. The slope of the curve at specific points, instantaneous rate of change, so on and so forth. For the sake of what we're going to do, take this equation here. Instead of y equals x squared, remember how y and f of x are the same, as long as this is a function, which it would be. Rewrite this as f of x equals x squared. It'd be a little bit easier to see sort of what we're doing. Do that. I'm just zooming in here. Give me 1 second. Make sure we can see this. In order to find a derivative, this is the formula for a derivative. So over here, we're going to just rewrite that formula. So rewrite this out. So basically just copy this thing here. In order for us to find a derivative, we need to basically plug into this formula. Well, f of x we know. So we're going to be taking f of x, and we're going to be plugging this in for f of x. So the x squared is going to go right here. What we would still need is the f of x plus h. So if I come over to this function, let's say I wanted you to find f of 2. Don't write this down. But if I wanted to find f of 2, you would just take 2, plug it in for your x, square it, that's f of 2. If I wanted f of 5, then you would just plug your 5 in, square it, that's f of 5. Well, what we want, so that we can plug into our little formula over here for a derivative, is we want f of x plus h. So just like you would have done with your 2 and your 5, you're going to replace your x with an x plus h. So it's just a regular old composite function. It looks kind of weird. Instead of x, it's x plus h. So instead of x squared, it's x plus h squared. With these now set, we're going to come back over to our formula here, and we're going to plug those in. So f of x plus h, you're going to replace with this, minus f of x for this problem is equivalent to x squared, all over your h. From there, this is just a regular old limit problem like we would have been doing the last few days prior to, well, not the last few days, but the quiz that we took here a few days ago. Ideally, what we can do is take your h as a 0 and substitute it in for your h's. But what you'll see is when I take my h and plug it in here, you're going to get a 0 in your denominator, making it undefined. So our first option with any limit was to substitute in. The second option with any limit is to simplify it and then substitute in. So that's what we're going to try and do. We can't plug in. So we're going to clean this up. So we're going to square this out. So x plus h quantity squared would be x squared plus 2xh plus h squared minus x squared. And then all of that gets divided by h. So that's currently our problem. What you'll see now is we should be able to simplify this a bit, because what we end up with here is an x squared. We're going to be subtracting that x squared. Those guys are going to cancel each other out. So in the next step, if those are canceled, look at what we would have left over. In this spot, we have a 2x plus h. This spot, we have h squared. These are gone. So these two here have a common h. See how this has an h that has two h's? So we're going to take these two, we're going to factor out an h. So pull that h out. Gives you a 2x. Here we would have just the one h left over, and then all of that is still divided by that h that was in our denominator before. What you'll see is, once we pull the h out from those two here, we can now cancel this out. The h's are going to be gone. So kind of like the problems we did a little bit ago, once we've eliminated that problem, now there's nothing stopping us from taking our h's as 0 and plugging it in. So now the h is gone here. Let your h here become a 0. I'm going to write one more step with this. So I'm just going to go one more step with this completely simplified. I just have 2x plus h is what that simplified to be. So now let your h become a 0 here. Again, just Just regular old limit, plug it in. The h is becoming a 0. What you would be left with is, if that's a 0, the only thing left over is 2x. That is your answer. That is your derivative. Now, looking up, actually we skipped this, didn't we? Look for your notation for a derivative. See how the y has a little tick mark here? That's a derivative notation. So this means y, this is read as y primed. That means that's the derivative of y. Same here, this would be f primed. That's the derivative of x. Other ways to write derivatives are either with dy dx. Right, dy dx kind of is the same as change in y over change in x. But the reason we don't want those deltas is deltas implies you're doing it over an interval. And what we set up here is, at the top, our intervals are getting so small that there really is going to be just a tangent line and there is no interval left over. So instead of changing x over, or changing y over changing x, it's just going to be written as dy dx, but kind of meaning the same thing. And then the last one would just be the derivative of whatever in terms of x. So since these are our derivative notations, notice how we started out with this equation. Now that we've taken the derivative of this, we would say that this would equal y primed. That is the derivative. This is the derivative of y. So this is our original equation. That is your derivative. Okay. What does all this mean is probably what we're asking right now. So let me try to explain that here. Here's our graph, x squared. What we said a derivative means, it's the slope of the curve. What's going to be different about this now, I think I mentioned this earlier if I remember correctly, instead of just being able to find the slope of lines, this parabola actually has slopes also. And what we want to know is, what is the slope of the parabola anywhere we want it? That's the slope of the parabola anywhere we want it. So let's say I was over here at x equals a -2. If I were to kind of draw in a line here, what kind of slope would we have here in terms of positive or negative? Well, this line is going downwards. It would have a negative slope because at x equals a -2, if I plug it into my slope formula, the derivative formula, I'm going to get a derivative of a -4. What that means is that's the slope of the graph at that particular point. If I go here, my slope here should be 0. Well, take that x value here, which is a 0, plug it into that little formula we just got, and this is going to tell us that our slope equals a 0. Over here, my graph is increasing. If I draw a tangent line in at this point, let's say this is 2, I should have a positive slope here. So if I took this x value of 2, plug it into my slope formula, the derivative formula, that's what that's going to give us, is a positive slope of 4. So this here, this little equation, will give us the slope of this graph anywhere we want it. If I want to know how quickly that graph is increasing at 10, first it'd be way up here as we increased. I would just take 10, plug it in, and my slope would be 20. That's how quickly that graph is moving at that point. All right, so that's what this gives us when we do the derivative. We'll be able to find slopes of sine curves, cosine curves, so on and so forth, anything we want, okay, using this little guy. All right, good. With that in mind, flip, and we'll do the next one. So again, our formula is this. Where do we want to start at? Let's start over here. Here's our formula. Limit is h goes to 0 with the f of x plus h minus f of x over h. Our function is 3x squared, so we're going to be taking this, plugging it in here. What we would still need is the function with the composite of x plus h. So take this function. Our inside is going to be x plus h, so this is going to be 3 times x plus h. And then we're going to square that. Just plugging in that for your x. So now we can come over to this formula. Alright, and we're going to substitute in the stuff that we just found. So the f of x plus h in this problem is here. So you're going to do 3 times x plus h quantity squared minus f of x. In this problem, f of x is 3x squared. And then all of that is divided by your h. Okay, so all of them get divided by the h up here. So you can't see that again. There. H can't be plugged in as a 0 because you'll get a 0 in your denominator. So the next option is to clean this up. So we're going to, again, square out that quantity. So the limit as h goes to 0. So 3 times we square that, so x squared plus 2x h plus h squared, and then minus 3x squared. All that divided by h. I'm going to distribute the 3 to everything. So limited as h goes to 0, I'll get 3x squared plus the 3 times the 2, 6xh, plus the 3 times the h, 3h squared, and then minus 3x squared. All of that divided by h. Alright, what generally is going to happen with these, and it happened in the last one, is something should simplify so that we can cancel some stuff out. So in this case, your 3x squared's gone, gone. And then notice again, we have a common h in these two. So we're going to pull out that common h. Rewrite everything. I'm going to pull out h from these two. And what I would have left over here is a 6x plus 3 and then just an h here. So 6x plus 3h. And then all of that gets divided by h. Okay? Those cancel. We should now let our h become a 0. So this is what we're left with, 6x plus 3h, and our h becomes 0. The only thing that we would be left with is 6x, which means, see how this started out as f of x? The way we're going to show that if f of x is 3x squared and this is our derivative, we would say f primed of x. That's how we would write our derivative. Okay? That's our answer. What this gives us is we can use this equation now to figure out the slope at any point on this particular parabola. Alright, that's what we just got. Okay, hey, don't worry about this point right now, but take a minute, see if we can go through and get the derivative for 5x squared. Yeah, and before you ask, yes, you need to show all the work. Alright, that's all I'm going to say. So go through, find that. I'll do it here, but take a minute, see if we can get through all of that, and find our derivative. And then we'll talk about what this point means here in a second. So go through that for a second. This is your f of x plus h. Make sure we get started right. So your limit h goes to 0. This is our f of x plus h minus the f of x all over h. Alright, so go through and see what we get. X. Anybody? Hopefully. Should be 10x. That's your answer. So if our derivative is 10x, what you would say is f primed of x should equal 10x. This is what we should have ended up with when we simplified, but the h becomes a 0. So 5 times 0 is 0. You're just left with your 10x. In the previous couple, 6 and 7, up here on the previous page, this was your final answer. When I now give you this point, what this is saying is I actually want to figure out the derivative at this particular point. The formula we just found, this gives us the slope anywhere we want here. We want to figure out our slope at this exact point. So the way we would show that is we would now just say f prime of, see how there's an x in your derivative? Well, look at your point. The x coordinate at that point is a negative 1. So we would say we want to know what is f primed of negative 1, because that's the x coordinate in our point here. So take your negative 1, plug it in, 10 times your negative 1 should give you a negative 10. So what this means is at this point would be on the graph, at this point on this parabola, that is your slope. All right, negative 10. So our graph is decreasing at a rate of negative 10, and then we could say like feet per second, meters per second, whatever, when we start using those words. Okay? All right. Number 9. Set this up. First, f of x plus h should equal 2 times x plus h squared, but we also now have a minus 1, so for the first time we have a binomial. But here's your f of x plus h, that's your f of x, so we're going to plug that in. So you're going to have 2 times x plus h squared minus 1, that's your f of x plus h, minus f of x, which is the 2x squared minus 1. All of that gets divided by h. Next, we need to clean that up so that we can let our h become 0, hopefully. We're going to distribute this out, so you're going to have 2 times x squared plus 2xh plus h squared, and then minus 1. That part. Minus this, not a whole lot we can do with. We're just going to leave that as 2x squared minus 1. All divided by h. We can distribute here, so that's our next step. Make these fun, nice and short, fun stuff. Distribute 2x squared plus 4xh plus 2h squared. That's just us distributing here. We still have the minus 1. We're going to go ahead and take this negative and distribute in here. So minus 2x squared plus 1, all divided by h. Then, a few things cancel out. This 2x squared would cancel out with that minus 2x squared. This negative 1 would cancel out with that positive 1. We're just left with 2 terms now, these two. Notice, shockingly, they both have an h in them. Just like the previous 3, we're going to pull that h out with the h here so that these will cancel. We can now take our h equaling 0. If the h becomes a 0, this would go away, and the only thing you would be left with is 4x. This is your derivative. Okay? However, if you look up here, a little more information I wanted this time. 7 up here, all I wanted was your derivative, that's it. That's the derivative of our equation. 8. Not only did I want the derivative, I wanted you to use this to then actually find the slope value or the derivative value at a certain point. In this point, negative 1, 5. In this case, I want you to find the derivative of our equation, and then you're going to write the equation of the line tangent to the graph at 2. What that means is, if I were to graph this, here's your parabola for this. It has a vertex at 0, negative 1, and it opens up like this. Okay, I promise that's, if you graph that, that's this parabola. At x equals 2, so somewhere over here at x equals 2, we could draw a line that's tangent to the curve. So it hits the graph, and then looks like this. So that's our tangent line to this curve. What I'm saying in this sentence is to write the equation of that line. Well, the whole idea of a tangent line is a line tangent to a curve shares 2 things. They're going to have the same slope, same slope. Understanding your derivative is your slope, and they're going to share a point. Okay, so the x-coordinate of that point is a 2. We still need to figure out our y, and we need to figure out our slope. Once you have that, you're going to write the equation of your line. So this is the whole point-slope form. I'm going to write the equation of our line tangent to our curve. We know the x-coordinate of our point. I gave that to you. It's a 2. We don't know the y-coordinate at our point, but it should be pretty easy to figure out. We should be able to take 2, plug it in here. Here's what y equals this. So if I took a 2, plug it in, 2 squared is 4, times 2 is 8, minus a 1. Our y-coordinate here, do it here, is a 7. So let's do it over here. Our point is 2, 7. Still need our slope. That's what this gives us. The whole point in doing this is the derivative gives you the slope anywhere we want it. So I'm going to take our derivative. Notice how x is a 2. So f primed of 2 means I need to take 2, plug it into this. So if f primed of x equals 4x, then f primed of 2 must equal 8. That then is the slope of the curve. All right? Write your line, y minus 7, the slope we found to be 8, and then x minus 2. And then voila. Alright. Okay, 10. The graph of the function y equals f of x shown below. So this is our function graph, our original. I want you to graph the derivative on the blank coordinate plane. The whole key to doing this is understanding a derivative is now just a fancier way of saying the slope of the curve. Right. Derivative means slope. So we're going to take our function graph and we're going to graph the slope over here. So look at your function graph. It's just 4 line segments. 1, 2, 3, 4. All right, this one here, you can see this. What we want to figure out is what is the slope of that line? Well, if you look at your graph here, to get from this point to this point, you're going to go down 1, right 1, down 1, right 1, down 1, right 1, which means your slope is a -1. The reason that is important is because we're going to come over here, graph our derivative, and the derivative is your slope. So notice how this line starts at a -5, ends at a -2. So from a -5 to a -2, if we're going to graph our derivative is always a -1, meaning here's what this would look like. It's just always going to have a y value of a -1, starting at -5, finishing up at a -2. So that's what that would look like. Go to your next line segment. The next line segment starts at a -2 and goes to 0. Well, this slope, if you look, to get from this point to this point to this point, you're going to go up 2, right 1, up 1, 2, right 1. So the slope of that line should be 2. So on the intervals from a -2 to 0, so from here to here, we should always have a value of 2. So that would look like this. From 0 to 2, our slope would be down 1, 2, 3, right 1, down 3, right 1, so a -3. So the slope of this line is a -3, and that starts at 0, ends at 2. So here's 0, here's 2. You should always have a value of -3. Last one, this line, you go up 1, right 1, up 1, right 1, so the slope is 1, and it's going to go from 2 through 4. So from 2 to 4, we should always have a y value of 1. Okay. That's our derivative graph. It's just the slope of this graph anywhere we want it. Got it? Great. Moving on. The never-ending notes. All right. 11. I want you to graph y equals x squared. So 0, 0, 1, 1. If x is 2, y is 4. If x is 3, y is 9. So we're just plugging it in. If x is a -1, you plug it in. A -1 squared is 1, so -1, 1. -2 squared, 4. negative 3, 9. This should be our graph. Let's see my beautiful artistic abilities. Missed that dot completely. That's awesome. Alright, there's our graph. Alright, find the equation of the line tangent to the graph at y equals x squared. And here, we've already done this derivative. It's the very first one we did, so if you need to look back, feel free. But y equals x squared we've already found. We found our derivative to be 2x. Now, the difference is I want to write the equation of the line tangent to the curve. So what we need to figure out is, what is the derivative value at this point? Well, what we do is just do 2 times x. In this point here, your x is a 2. So I want my derivative value at 2. So I'm just going to plug in a 2. And my derivative value is 4. Keeping in mind, your derivative is your slope. So that really is the slope of our line. So you have your slope, the slope is 4, you have your point, it's 2, 4, we can write our equation. So using this point, that slope, I'm going to do y minus 4 equals 4 times x minus 2. We want to graph this line over here on the graph. So to do that, we're going to put this in the slope-intercept form. So go ahead and distribute. Add your 4 over so that this is easier for us to graph. And graph that line. So you're going to have a y-intercept of a negative 4 here. Our slope should be 4 also. So from this point, you're going to go up 4, 1, 2, 3, 4, right 1. And then the same thing again, 1, 2, 3, 4, right 1. Notice how we're hitting this point. We should share one point on this graph, and it's the point 2, 4. So we better hit that point. One more time, 1, 2, 3, 4, right 1. Alright, as best you can, connect those. And what I want you to do, and it should be pretty obvious on mine and on yours, is right around the point of tangency, the point 2, 4, that we use to write the line tangent to the curve, where the line actually hits the curve. Right around this point, if you kind of look in this general area, it's going to be hard to distinguish the line and the parabola. They're going to be pretty much the same. So the y values on each of them, the y value on the parabola, the y value on the line, should be pretty similar to each other. Okay? That's what this gets at. And this is why we write lines tangent to the curve often, is because we can actually use the line to figure out what y values would be on that curve. It's an approximation. They should be really close, but that's what we can use. So 13, you graphed it. What I want you to do is find f of 1.2. Well, f is the original equation. Here's our function, x squared. I want you to find, did I say 1.2? F of 2.1. So you're just going to take 2.1, square that, and that will give you f of 2.1. Alright? So that is the y value on your parabola. Alright, so that should give you, I think I be safe here, so that'd be crazy. 4.41. So on our parabola, the parabola is f of x. We would get a, at 2.1, if we just move a little bit, 4.41. Now, use the line, so here's my line. We want to do the same thing. We want to figure out what is our y value on the line. So let's use our line. Here's our line. And we want to plug in 2.1. So y equals 4 times 2.1 minus a 4. Y would equal 4.4. Notice how close those are? That's why we can use a line to approximate a value on the curve if it's a tangent line. So we were sharing a point at 2, 4. So notice how we barely moved off of that point. 2.1 is not far away from 2. That is why their values are still very, very similar. They're both right around the point where pretty much the graph and the line are right on top of each other. Same with 1.9. 1.9 would be just off of this point. So if I found f of 1.9, that means I'm going to take my function x squared, plug in 1.9. And 1.9 squared, and we do that, should give us 3.61. Then you're going to use your line. So again, here's your line. Y equals 4x minus a 4. We want to figure out what that should be. Since you were hitting your curve at 2, and we're only at 1.9, again, 1.9 is incredibly close to 2, so it's like right here. And at 1.9, the line and the parabola should be almost the same value. So when we go ahead and find that, so let's do this, 4 times 1.9 minus 4, that gives us 3.6. So notice how close those are, okay? So that's again why we find tangent lines. We do this a lot throughout the year, and it's because we can use that to approximate values on the curve. All right, 18. F of negative 3. Function is x squared. Our functional value that I want is at negative 3, so your y value would be a 9. Using your tangent line, we want to approximate that. So again, take your line, 4x minus a 4, plug in negative 3, and what you get your y value to be is a negative 16. So, okay, hopefully you can see that because my computer just died. 9 is what you get for f of negative 3. And when we use our line to plug in the negative 3, you're going to get us negative 16. And then I asked the question, why is there such a disparity in values? Because the ones we did up here, the functional value and the line value were incredibly close. Same here. The functional value and your line value were incredibly close. Now the functional value and the y value are nowhere close to each other. All right. Well, the reason for that is the point where we're tangent to the curve is here. I wanted you to find f of negative 3, so we're actually finding values at a negative 3. So that's why negative 3, you're way up here on the curve. The line would be way down here. All right. So the only time we can use our line to approximate values is if we stay really, really close to the point where the line hits the curve. And negative 3 is not close to that point. That is why there is such a disparity. Okay? So when it says why is there such a disparity, I would say this. Because x equals a negative 3 is not close to the point of tangency 2, 4. And therefore their values are not necessarily going to be the same. Okay, the never-ending notes have ended. Until tomorrow.